At Aero 2017, UTC Hubble's WFC-3 logged a 2 milliarc-second kink in 3I Atlas track an instantaneous lateral acceleration not away from the Sun but straight toward Jupiter. Navigation filters flagged the residuals. Gravity-only ephemerides snapped out of tolerance. A faint, persistent push emerged in the data aligned with the Sun-Jupiter line. One instrument, one moment, one impossible shift. On the sky, a dim interstellar ember slid across the constellations, its path curving toward the gas giant's domain. Normally, an object like this would arc under the Sun's pull flare gently as sunlight heats its surface, and drift on an ice and rock messenger passing through. But 3I Atlas bent more than it should have. Scientists read that deflection as a signature of non-gravitational forces, and the implication was immediate. Something was pushing. Across the world, NASA, ESA, JAXA, and CNSA teams synchronized their watch lists while amateur astronomers tightened the timing from backyard skies. Spectral measurements tell us what vapors escape: an object water, carbon monoxide, strange organics, by the colors they imprint on light. Coronagraphs on ground telescopes, which block a star's glare to reveal faint companions, were retuned to isolate 3I coma. The goal was simple. If jets were thrusting, we should see their fingerprints. Data streams revealed an anomaly familiar, yet wrong. We have seen non-gravitational nudges before Oumuamouas, puzzling drift 2I Borisov's cometary jets. But those pushes point roughly away from the Sun as ices sublimate. Here the vector leaned toward Jupiter. Some teams argued it was geometry, a transient jet just lined up by chance. Others doubted the readings entirely pointing to Hubble's roll angle and background stars. But then the VLT and Subaru confirmed the same skew. Modelers turned to Jupiter, and stakes rose. If 3I Atlas skims the planet, it could seed waves in the upper atmosphere, stir auroras, or even fragment a Shoemaker-Levy echo with interstellar chemistry. To understand why this matters, we need to look at how giant planets sculpt systems they are gatekeepers, and encounters rewrite trajectories. History answered with collaboration. The spirit of Voyager and Galileo returned. As Juno tuned its instruments, Alma probed for exotic gases, and radio arrays from Spain to South Africa hunted for dust. Theories multiplied. Exotic outgassing, a cometary sail made of porous dust, even electromagnetic coupling in Jupiter's vast magnetotail. Why would an interstellar object behave like this? As tension built, one pattern refused to yield to explanation. Over 36 hours, independent observatories reported the same unsettling geometry. The non-gravitational acceleration held nearly constant in strength, yet kept rotating to stay within a degree of the Sun-Jupiter line. The alignment held through another dawn. Normally, a comet's tiny rocket thrust from outgassing points roughly away from the Sun, and wobbles as jets switch on and off. But 3I Atlas refused that script. Its extra push kept swiveling to cling to the Sun-Jupiter line as if tracking an invisible rail. Teams at NASA and ESO ran quick checks. No obvious instrument bias. No shared software bug. If it was not gas or light alone, what was steering it? The spectra came back oddly quiet. Spectral measurements tell us which molecules are escaping because different gases leave fingerprints in reflected sunlight. Here, the fingerprints were faint. No vigorous water or carbon dioxide lines. No brightening curve you would expect from a lively comet. Solar radiation pressure could nudge a very light object echoes of Oumuamouas mystery, but that force always points away from the Sun, not toward a moving line stretching to Jupiter. This was different. A change in the solar wind added a clue. ESA's solar orbiter and NASA's coronagraphs, which work by blocking the Sun's glare to reveal the surrounding plasma, saw a subtle kink propagate through the heliospheric current sheet as Jupiter rotated into view. JAXA's Hisaki recorded a modest uptick in Jovian auroral power, the kind triggered when the magnetosphere reconnects with the solar wind. If 3I was electrically charged, even slightly, a large-scale magnetic field could in principle impart a gentle, persistent shove. Could a visitor from another star be surfing field lines drawn taut between our star and its largest planet? The community split along familiar fault lines. Planetary dynamicists cautioned that fields this weak rarely move rocks. Plasma physicists countered that in a tenuous ionized sheath, charged grains behave more like dust than stone. Some groups, including a CNSA-led team with fast radio support, pointed to coincident low-frequency noise near Jupiter and argued for an electromagnetic coupling. Others doubted the readings entirely, reminding everyone that coincidence is not causation. Simulations sharpened the stakes. Feed a constant, slowly rotating acceleration into the trajectory, and the path bends subtly at first, then inexorably toward a Jovian encounter corridor. Navigators at JPL and ESOC do not scare easily, but they do respect compound errors. Non-gravitational forces complicate predictions. If fields can steer an interstellar object, how many of our comfortable assumptions need revisiting? History whispered warnings. We have not seen something like this since Oumuamua hinted at radiation pressure physics. Yet 2I Borisov looked blissfully cometary. 3I Atlas now sat between those precedents, a compass needle seemingly pointing to Jupiter. Why would an interstellar object behave like this? And what hidden mechanism could sustain such a lock? And here is where things take an unexpected turn. As amateur networks from Chile to Namibia refined astrometry, and Junos watchers scanned for auroral echoes, a new pattern emerged. Subtle, repeatable, unsettling. Moments like this remind us how little we truly understand. But this was only the beginning. A strange cadence appeared in the data, brief, brightening pulses that lined up with flips in the solar wind's magnetic field. Normally, comets brighten in a smooth arc as sunlight warms their surface and jets switch on with the day-night cycle. Here, the spikes ignored the sun's clock and followed the Parker spiral, the helical magnetic scaffold. The wind drags through space. Some teams argued this pointed to charged dust coupling to the interplanetary field, as if the object were being tugged sideways by space weather. The implication was unsettling external steering, not just internal outgassing. Subtle course deviations arrived right on cue with those pulses. In a clean gravitational model, the trajectory should curve predictably under the pull of the sun and planets. Instead, astrometric residues nudged in directions that rotated with the field, not the sunlight. Dynamical groups at NASA and ESA added a tiny Lorentz-like term: what happens when charged grains feel a magnetic force and the fit snapped into place. Why would an interstellar object behave like a magnetosail? Coordinated observatories went hunting for proof. A coronagraph blocks the sun's glare so faint, halos can be seen, and both SOHO and Solar Orbiter watched for ion tails that kink with field lines. JAXA's Hisaki scanned Jupiter's ultraviolet aurora, while Junos instruments listened for any magnetic whisper traveling down the line. Usually such cross-planet connections are seen with Ios volcanic plume. This time the timing was new, weak repeatable echoes matched 3I Atlas pulses. Solar physicists were divided. Some called it coincidence. Others saw the fingerprints of field-aligned flows. Spectral measurements added color to the pattern. Spectrometers split light into fingerprints, and 3I Atlas showed fleeting signatures of sodium and hypervolatiles, the kind that sputter under particle bombardment. Typically, that chemistry blooms closer to the sun. Here, it flared early in sync with solar wind sectors, suggesting that plasma, not sunlight, was flipping the jets on and off. It echoed the puzzle of Oumuamua's non-gravitational shove, but with a clearer agent-charged dust and ions. Global models took the next step. When teams from CNSA's planetary group JPL and ESA's operations center folded a changing magnetic field into their simulations, a new route emerged, a slow drift along the spiral into Jupiter's magnetic footprint. In a purely gravitational world, this aiming should not happen. With intermittent charge and a porous, lightweight surface, it could. Others doubted the readings entirely, reminding everyone how easily noise masquerades as signal. And then something even stranger emerged. Radio arrays in South Africa and Chile picked up faint periodic scattering like a rotating lumpy coma acting as a sail that keeps finding the same wind. To understand why this matters, we need to look at what Jupiter represents: a colossal magnet and a deep gravity well. If space weather can herd an interstellar object toward that, well, what else in our sky is quietly steered by invisible currents? Moments like this remind us how little we truly understand, but this was only the beginning. A week after the first hints of a cometary sail, a violent solar storm rolled off the sun, and the object's path kinked subtly toward Jupiter. Normally, a comet's track is a smooth curve shaped by gravity and a steady push from sunlight. This one jumped after each coronal eruption. Coronagraphs, telescopes that block the sun's glare to reveal the corona caught the blasts ground teams watched 3I Atlas brighten out of sequence. Scientists read the pattern as a coupling space weather was not just buffeting the coma, it was steering the thrust. A sudden shift in the spectrum sealed the suspicion. Spectral measurements tell us what a comet is doing by the light its gases absorb and emit, and the lines from ionized molecules grew sharp, while neutral emissions lag. Normally, comets brighten in a predictable curve as ices sublimate here, charged gases and dust spiked right after each shock hit. The difference mattered. Charged grains feel the magnetic field carried by the solar wind, and when outgassing is asymmetric, that magnetic tug can bias the tiny rocket effect. The interpretation was bold. The coma was a sail, yes, but a magnetized sail catching gusts that arrived on schedule. A global scramble followed. NASA's Parker Solar Probe and ESA's Solar Orbiter mapped the storm fronts. JAXA's Hisaki watched Jupiter's auroras surge, a sign its magnetosphere was linking to the solar wind. Juno's radio instruments heard the crackle of reconnection. Multi-continent telescope arrays from Chile to Hawaii to the Canaries synced their clocks. Amateur astronomers from Poland to Peru caught the ion tail snapping into the same direction after each event. Solar physicists were divided. Some teams argued it was just radiation pressure plus anisotropic outgassing. Others doubted the readings entirely. But the correlations tightened round after round. A clearer picture emerged. Sector boundaries in the interplanetary magnetic field were threading into Jupiter's vast magnetotail, building a temporary magnetic runway. Each time a shockwave passed, the field lines reoriented, and the ionized coma felt a sideways pull, nudging the rocket thrust a little closer to Jupiter's lane. Gravity did the rest. It was subtle, cumulative, and yes, a little terrifying, because it means giant planets can reach out through storm-fed fields and herd interstellar visitors. If space weather can lay invisible tracks, what else in our sky is quietly riding them? A memory stirred Oumuamua's gentle, unexplained push. 2I Borisov, the normal interstellar comet, and now 3I Atlas, revealing the missing context plasma magnetism timing. Moments like this remind us how provisional our maps are, how many threads we do not yet see. The collaboration grew, quiet, resolved. The mechanism was in sight, and Jupiter, patient and enormous, was waiting. The turn came during a quiet crossing of the heliospheric current sheet, the vast wavy surface where the sun's magnetic field flips direction. Normally, an interstellar visitor simply follows gravity with a little extra shove from outgassing. This time, the ion tail kinked, as if caught by a hidden current, and the trajectory pivoted toward Jupiter's longitude. Teams reading the models said the timing with a correlating interaction region, denser, faster solar wind sweeping past, acted like a magnetic gust. The implication was unsettling. Space weather did not just paint the sky, it nudged a world-sized rock. A burst in brightness arrived just after a coronal mass ejection captured in stacked frames from ESA's Solar Orbiter and NASA's stereo coronagraphs. A coronagraph works by blocking the sun so faint structures around it can be seen, and what emerged was a sudden halo thick with ions. Normally, comets brighten in a predictable curve as sunlight warms their ices. Here, the spike lined up with an uptick in solar wind density and field strength. Solar physicists were divided. Some saw textbook coupling, others warned of coincidence and processing artifacts. But the timing kept holding. Spectral measurements told us what the eye could not. Across multi-continent telescope arrays, sodium lines flared and ionized, carbon surged, JAXA and CNSA instruments confirmed the same pattern. Usually those lines trace gentle sublimation. In 3I Atlas, they came in pulses matching the rotation and hinting at jets that switched on when magnetic field lines draped the coma. If jets push asymmetrically, they steer. If the field guides the jets, the steering can become directional. Why would an interstellar object behave like a weather vane? Juno felt the prelude before we did, recording a restless magnetotail as Jupiter rotated into the sector where 3I Atlas was headed. To understand why this matters, we need to look at Jupiter not only as a gravitational giant, but as a magnetic one. Its enormous magnetosphere is a moving target and a catchment. Some teams argued this pointed to a magnetic assist, a corridor that increases the odds of a close pass. Others doubted the readings entirely, reminding us how rare these alignments are. History echoed softly. Oumuamua's gentle, unexplained push, to Borisov's plain cometary honesty, and now a third-act plasma magnetism timing conspiring with Jupiter. The terrifying part is not doom. It is agency. If solar wind structures can shepherd interstellar objects toward giant planets, then captures and slingshots are not random storms, but seasonal tides. Moments like this remind us how little we truly understand. And here is where things take an unexpected turn. The corridor was not closing. It was sharpening. The corridor sharpened as 3I Atlas crossed a seam in the solar wind, its tail tightening and its brightening curve flattening. Normally, comets glow more fiercely as they fall inward. Here, the light steadied, while the tail became a thin, disciplined ribbon. Scientists read this as grain sorting by magnetic fields. Larger dust falling behind smaller charged particles guided ahead, turning a broad wake into a nozzle. Coronagraph images from SOHO and Solar Orbiter revealed a persistent braided streamer pointing toward Jupiter's longitude. A coronagraph works by blocking the sun's disk, so faint structures in the corona stand out. Normally, those streamers sway like laundry in a gust. This one held its pose rotating with the sun, a co-rotating interaction region that looked suspiciously like a lane. Parker Solar Probe and ESA's Solar Orbiter registered switchbacks, sudden flips in the magnetic field, arranged along Atlas path. Switchbacks are kinks in the interplanetary magnetic field, like snapped whips in the wind. In this case, teams argued the nucleus was magnetically draped, turning its dust coma into a soft sail that nudged it laterally toward Jupiter's waiting gravity. Trajectory solutions from NASA's, JPL-ESA's, ESO-JAXA's, ISIS, and CNSA's Deep Space Network began to converge instead of fray. Ordinarily, outgassing adds jitter and widens the future cone. Here, either the jets quieted or they aligned with the course, shrinking the uncertainty. The implication was unsettling. Capture is not a dice roll, it has seasons. Spectral measurements from Keck VLT and Subaru showed muted ice bands and an excess of metal-rich dust. Spectral measurements tell us composition by reading the fingerprints of light. Unlike Borisov's classic cometary mix, Atlas seemed crusted, more resistant, and more easily coupled to fields. What hidden mechanism could produce such a transition mid-journey? Solar physicists were divided. Some teams argued this pointed to magnetic flux ropes acting like rails, with co-rotating regions steering as the sun spun. Others doubted the readings entirely, citing calibration drift and line-of-sight tricks. Then, amateurs from Spain to South Africa to Australia logged synchronized tail angle flips at solar sector boundaries, and the doubt softened. The pattern echoed history Jupiter as gatekeeper. We have not seen something like this since Shoemaker-Levy 9's Capture and Ruin, and the interpretive fog recalls Oumuamua's quiet, non-gravitational whispers. Normally, a planet is just gravity, but Jupiter's vast magnetosphere and bow shock can shape plasma like a harbor shapes tide, adding intent to pull. As Jupiter rotated the lane, narrowed to a thread, the giant's magnetodisk spokes sliding into alignment with the solar wind's groove. To understand why this matters, we need to look at agency in a clockwork sky fields, particles, and timing writing fate. Why would an interstellar object behave like this? Because the ocean between stars has currents, and Atlas found one. The lane tightened to a thread, and observers noticed that each nudge in Atlas' path seemed to arrive on Jupiter's beat. Normally, an interstellar visitor is ruled by gravity, and the gentle push of outgassing, nothing else, has a strong enough hand at such distances. But this case was different. The deviations came in sync with the giant's rotation, as if a faraway lighthouse were tugging the wake of a tiny boat. Scientists began to interpret the pattern as electromagnetic steering, and the deeper implication was unsettling. Planetary magnetospheres can reach across space and change what should be a simple Keplerian fate. A sudden ribbon appeared in coronagraph images, faint but persistent, pointing along the solar wind toward Jupiter's night side. A coronagraph works by hiding the sun's blinding disk, so the thin, ghostly structures of the solar wind become visible. Normally, those streamers sway like loose silk. Here, the filament aligned with the direction of the Jovian tail. ESA's solar orbiter, NASA's SOHO and STEREO teams argued this pointed to a temporary magnetic highway. Skeptics called it a trick of projection. If the connection was real, it meant field lines and charged dust were writing a new kind of trajectory. Spectral observers then reported a pulse lines from ionized sodium and cyanogen brightened and faded on a 10-hour cadence. Spectral measurements tell us what atoms and molecules are present and how they are energized. Normally, comets brighten in a predictable curve as sunlight and heating increase. This one flickered to Jupiter's rhythm. Solar physicists were divided. Some teams argued this was Lorentz drag acting on charged grains, tiny particles feeling a sideways force in a magnetic field. Others doubted the readings entirely. What hidden mechanism could produce such a transition? Juno's instruments registered changes in the current sheet, the wide, flaring magnetodisk, while JAXA's Hisaki saw shifts in ultraviolet auroral glow. Ordinarily, reconnection in Jupiter's tail tosses plasmoids outward. This time the timing lined up with Atlas course corrections. NASA, ESO, CNSA, and JAXA groups stitched solar wind data from Parker Solar Probe to Earth-based arrays from Atacama to Mauna Kea and La Palma. The interpretation that emerged was simple and chilling, adding intent to pull. Amateurs across 3 continents contributed light curves that caught the flicker when the big observatories were clouded out. This echoed the mystery of Oumuamua's non-gravitational push, but with a conductor Jupiter holding the baton. We have not seen something like this since 2I Borisov reminded us that interstellar visitors can be ordinary. Here was one that was anything but. Modelers then reran the ephemerides with an electromagnetic term and found a narrow window where the magnetotail could herd Atlas sunward and then downslope toward Jupiter. Why would an interstellar object behave like this? Because the ocean between stars has currents, and Atlas found one. Moments like this remind us how little we truly understand. If a planet can cast a magnetic net, our planetary defense playbook is incomplete. And this was only the beginning. The verdict arrived not as a single paper, but as a chorus Junos magnetometer, Parker Solar Probe ESA's Solar Orbiter, and JAXA's Hisaki, all pointing to the same unsettling mechanism. Normally, a comet's path is written by gravity and a bit of gas thruster from sunlight. This time something else was steering. The teams concluded that 3I Atlas carried magnetically responsive dust and supervolatile ices, turning it into a reluctant plasma sail. The why is simple to state, hard to accept. Jupiter's magnetotail caught it. The telltale came first in the light curve. Normally, comets brighten in a predictable curve as they warm. Atlas brightened in pulses that lined up with solar magnetic sector crossings, the invisible lanes in the heliospheric current sheet. Solar physicists were divided. Some argued it was coincidence and calibration drift. Others said this was the signature of charged grains coupling to the wind. To understand why this matters, we need to look at how a coronagraph works. By blocking the sun's face, it reveals faint outflows. In those images, Atlas coma kinked exactly when the magnetic lanes shifted. The composition sealed it. Spectral measurements tell us what molecules and minerals are present by how they absorb light. ALMA and the VLT found carbon monoxide and nitrogen ices, plus a whisper of magnetite and metal-rich dust. Normally, those are minor notes. Here, the mix created a weak magnetic moment, as the nucleus rotated small but not zero. Polarimetry from amateur networks across 3 continents confirmed the grains were aligning in fields like tiny compass needles. And here is where things take an unexpected turn. Replaying the trajectory with those forces included NASA, ESA, CNSA, and JAXA teams found a narrow corridor through the solar wind where the heliospheric sheet funneled Atlas into Jupiter's wake. Gravity should have only nudged it, the magnetotail guided it. Some teams argued this pointed to a temporary capture into irregular Jovian space. Others doubted the readings entirely. Then Juno saw the bow shock of Atlas coma flicker inside the tail. Debate turned into agreement. The implication is the part that chills. If magnetospheres can herd interstellar debris, gas giants become nets and occasionally slingshots. That means objects can be focused into impact corridors or quietly parked among Trojan swarms without the usual gravitational warnings we rely on. This echoes the mystery of Oumuamua's non-gravitational push, but adds a steering wheel we had not considered. What hidden mechanism could produce such a transition? We just watched one. So why is Atlas headed for Jupiter? Because the ocean between stars has currents, the heliosphere has tides, and Jupiter cast a magnetic trawl across them both. Moments like this remind us how little we truly understand. Our planetary defense playbook will now need a chapter on space weather, not just rock and ice. And as amateur telescopes, deep space probes, and whole Earth arrays keep watch, we are left with a quiet, humbling thought. The cosmos is not empty space. It is a living sea, and we are only beginning to learn the maps.